All right, thank you very much. So good morning again, everyone. I'm David Edom, Federal Program Manager with the NNSA Office of Advanced Simulation Computing. I'll be the moderator for this morning's session. We have four presenters to start off our day. First, we have Alexandra Ballow from Montana State University. Her field is algebraic topology and quantum mechanics. Her advisor is David Ayala, and she did two practicums, both at Oak Ridge National Laboratory. Please welcome Alexandra.
Thank you. Good morning, everyone. Like he said, I go by Alex, so if you see me in the hallway, feel free to just use that. And I'm a pure mathematician, so algebraic topology is a field of pure math, and I also work with higher category theory as well. But I really tried to slow down the math a little bit, so hopefully this doesn't just feel like a slide of 25 definitions back to back. We can learn some about the physics as well. So what we'll be talking about today is anion systems, which are a key component of topological quantum computing. But to talk about anion systems, first we have to talk about what an anion is. So before I jump to anions, let's talk about bosons. Everyone's heard of bosons, but the key characteristic I want to make sure we're all on the same page about is when you switch two bosons, and you switch them again, there's no phase change. It doesn't pick up any phase. Fermions are the other one you've likely heard of. When fermions switch, they do pick up a phase. It's a -1, so when you switch them again, it's like nothing ever happened. The system is exactly as it started before. And the reason these are the two types of particles you've likely heard of, if you've heard of any, is because in almost every dimension, these are the only two options. I say almost because something really unique happens in 2 dimensions. And in 2 dimensions, if we take those same particles, make sure that they're stuck on like a plate or they can only move in those 2 directions, then they actually become anions, or they can become anions. So when you have an anion, if you switch them, they pick up a phase like the fermions. You switch them back, they still have a phase, and it's switched again. And this can continue to happen every single time you switch them. So as you're rotating around, you can kind of keep track of how many times they've got switched places. And because I'm a mathematician, I'm going to briefly talk about, but you've got to be wondering, what is it about 2? If I put those same particles in 59-dimensional space, this is impossible. This couldn't happen. So what is happening about these being 2 dimensions, and what the key, the linchpin in the argument that causes this is actually that the circle is not simply connected, and higher spheres are. Every sphere above dimension 1 is simply connected. And for those of you that have done any algebraic topology, this comes down to the configuration space of dots. So how dots switch if you can't tell them apart in place. That space has RPn minus 1. RP1, the fundamental group, is the integers. And for RPn higher than 1 is Z mod 2. So that Z mod 2 is where you're getting this -1 and 1. And then for RP1, you get the integers, which is why you can have so many different phase changes. So sorry, that was probably too in-depth, but it's really cool. This is why anions exist. And because anions exist, we can kind of leverage them. So let's look at a system more specifically. Now, anions are particles confined to 2 dimensions, like we just talked about, and they have a couple cool characteristics. If you have a particle and an antiparticle, it can split, and it kind of hears. You get 2 at once, but they always split into 2. If you have a particle and its antiparticle coming together, they called annihilation. I am not a physicist, so please excuse any difference in terms. Now, anions, I said it could have this differing phase, but of course that phase could still be 1 or -1, like the bosons and the fermions. We also want to kind of make sure we're in non-abelian systems so that when we keep switching it, we don't just get back to where we started. So let's do an example. So these are going to move very fast, and they're hard to track. It's hard to know what's going on. You saw some creation here, and then they annihilated up here. We'll do that quickly. But like, I can't follow what's going on. Even when I made it, and I'm still struggling to see how these dots are looping. So how can I take this system and be able to tell when they've merged? To do that, we're actually going to like lay our plate down and let it evolve over time. And we'll trace out strings where those dots are. And now we can really see how they're braiding and connecting. I'll turn it so we have more space. And because I'm a mathematician, I'm going to smooth everything out. No need for uneven edges. And now this, you can't really tell still how it's braided. These crossings, if all of these are over, this goes over the whole time, well then they didn't braid, they didn't switch spots. It just looks like it because I've smushed 3-dimensional space on a 2-dimensional board. So we'll also keep track of over and under crossings. So now we can see that this is actually a braid, this strand here. And so each time they switch, they pick up a phase, each spot here. And so we can keep track of how many times they've braided. We also see there's some annihilation there, and there's creation here. So we have all of our pieces of our system showing up in this little thing. And if you've done any math, especially knot theory, you might recognize that this is a tangle. This is a knot diagram. We got over and under crossings, it's strings all put together. Tangle just means you have a bunch of strings on either side, and then they can do whatever they want in the middle and twist, but the edges are fixed, which means we can leverage a rather strong mathematical result called the tangle hypothesis, which is now not a hypothesis, I think. It was proved a couple years ago by my advisor, actually. And so this tangle hypothesis says that there's a categorical equivalence, so just think equal as equal can be, between rigid braided monoidal categories, a lot of adjectives. Hopefully by the end, you're more comfortable with those adjectives mean, and tangles. So that means if we want to understand anion systems, which kind of look like tangles, then we want to understand rigid braided monoidal categories. Okay, like I said, that's a lot of adjectives. So let's go back and focus on the noun first. I hope that some of you at least have seen categories, and I'm going to criminally simplify them right now. There's objects, so here's some letters. There's morphisms between them, and these satisfy certain characteristics. We won't get into the characteristics now. Category theory is so simple that there are so many examples. Examples like this, for example, but also the objects could be every group ever, and the morphisms can be every homomorphism. This is an incredibly broad, it can be huge, it can be tiny, there could be one dot and no arrows. The examples are really never ending, which means there's a lot you can do with it. It's a really powerful structure. And to make it even more general, I'm going to add infinity category theory, infinity in front of it, change morphisms to one morphisms, change nothing else, and then I'm going to add 2 morphisms. So not only do I have objects and arrows between them, but now I also have arrows between my arrows. And there's no real reason to stop there. We can put arrows between our arrows between our arrows, and we can keep going. Now, I said I'm going to simplify categories, but here I truly am. The mathematician in me is a little upset just having this slide. Jacob Laurie has done a lot of work in infinity category theory, and he has 3 books, each of them well over 1,000 pages, just discussing an infinity category. This is more of like a sketch of what infinity categories are trying to achieve, and not really the mathematical structure they're using. So just know that this is like a gross simplification, but it should be enough for the talk, and it's also enough to know kind of what we're trying to achieve. So this infinity probably not very scaring all those scientists in here. So we'll jump back to just normal categories and we'll do our first adjective. So we're going to take this category and we're going to have a binary operation between it such that there's a unit. So if I take this binary operation and I take any object in my category or morphism and I tensor with the unit, then I should just keep that object on either side. Graphical calculus is kind of what's happening here is the interplay between that tangle hypothesis. On this side, we're talking about monoidal categories, and on this side, we have something that looks like tangles. So graphical calculus is a way to pictorially understand what's going on, so I'll have those for you on your right. The unit, we're just going to have no string at all, because if we tensor with the unit, nothing should happen, and then anything that's an object will have one string. Add another adjective, a rigid monoidal category, or autonomous, depending on what source you're looking at. It means each object in your category has a dual object. And when I say dual, I mean categorical dual, but vector space is an example. Vector spaces, so all the objects are vector spaces, and the morphisms are linear maps, is an example of rigid category because of the vector dual. So that is an example to hold on to if you have seen it before. And one of the key characteristics of this dual is that if you tensor an object with its dual, there'll be a morphism to the unit, and we'll represent that like this. You have your two strings on the left, and then there's no string on the right. Last adjective. If there's a braided category, there's an isomorphism if you switch the order of the strings. So graphically, that looks like this. And this piece right here is kind of where this infinity category theory, or the infinity part, is coming into play. Because if you have all of this information exactly the same, but the braid isomorphism is different between one category and the other, these are different braided monoidal categories. So we're not only saying that these two things are equal. If you've heard isomorphism before, it was like the same as equal. But when we're in category theory, we don't want equal to be the end-all be-all. We care about why they're equal or how they're equal, what isomorphism says they're equal. So now I talked about kind of the local system, but what if we had these anions on more three-dimensional shapes, on manifolds? Because it just needs to be confined to 2 dimensions, right? If it's confined to 2 dimensions on the floor here or confined to 2 dimensions on a donut out in the hall, it's still 2 dimensions. And how you do this is factorization homology, which I have nowhere near enough time to get into. But what it does is it takes a rigid braided monoidal category and it gives you a vector space. Now, a vector space is the observables of your system. This can help you kind of go to a global sense, but this hasn't been quite enough to fully understand the global observables. They were missing some, which my advisor affectionately calls ghost observables, because nobody could find them. Nobody understood why they were there. But if you take factorization homology and you infinityize it, like you, instead of looking at normal categories, you change everything to infinity categories, then these ghost observables do become visible. And how they become visible is instead of giving a vector space, if you've changed everything to infinity categories, you'll see you get a chain complex. And these ghost observables were actually coming about. You take that chain complex and take the zeroth homology, and then you're back to the observables. You get the vector space before, but you get slightly more. Because if you had something in the nth chain of your chain complex and the n-1, they could cancel and contribute to your zeroth homology. And that was what was actually happening to give these ghost observables. So this was like a very quick walk in the park through math, but if you actually want to understand and see the rigorous things behind it, I've included my favorite texts about category theory. These are the ones that I've kind of learned from, and a very, very readable survey of graphical calculus. If you really want to dive in and you're looking to get into pure math, this is Jacob Lorry's first book that I talked about. This one's about 900 pages, so relatively short for his works. But it was notoriously difficult to read, so he's currently rewriting it. I think he's about halfway done, and that's about 3,000 pages already. It's called Carradine. I should have put it up here, but and then if you want to jump even further, this is a source on factorization homology, which is going to use all of that information in Jacob Lorry's text, and I think higher algebra as well, which is the next in the series. Also like 1,500 pages, so got lots to read. I just want to thank everybody that helped me get here, my University of Montana State, and of course the fellowship practicum at Oak Ridge, which is where I learned more of the physics side of things. And to thank all of you guys for listening. Anyone has any questions?